In the winter of 1943, Los Alamos was a place where hope and dread lived side by side. Snow covered the mesas. Winds whistled through unfinished barracks. Scientists worked in isolation behind locked doors, each group given only fragments of the wider project. Even among the senior staff, only a few understood the problem that had begun to consume the laboratory. The plutonium bomb, the weapon intended to end the war, was failing before it was even born. At first, no one expected difficulty. The original idea had been simple, at least in theory. The plutonium bomb would use the same gun-type mechanism as the uranium design, a bomb that fired one subcritical mass into another like a bullet in a barrel. The concept was straightforward, reliable, almost comforting. Engineers believed that if uranium worked, plutonium would work too. They assumed the physics would behave. They assumed nature would cooperate. They assumed wrong. The plutonium arriving from Hanford in early 1944 revealed a truth no one had predicted. Its isotopic composition made it far more sensitive to spontaneous reactions. It could not be assembled slowly. If the two halves came together too gradually, the material would pre-ignite, causing a fizzle instead of a full nuclear explosion. The gun design that had seemed so secure for months collapsed in a moment of realization. The scientists gathered around the new measurements felt the shock like a blow. The plutonium weapon could not be built the way they had planned. Oppenheimer called an emergency meeting in the cramped library building that served as Los Alamos headquarters. The room was dimly lit, filled with chalk dust and cigarette smoke. The faces around the table were tense. The problem was presented plainly. The gun design will not work. The plutonium will pre-detonate. We need a new method. The words carried the weight of disaster. One bomb could still be built with uranium, but the plutonium bomb was supposed to be easier to produce, less dependent on rare material, and central to the whole strategy of the Manhattan Project. Without it, the project risked falling behind schedule. Without it, the war might drag on. It was in that meeting that Seth Nettermeyer mentioned an idea he had been considering quietly for months: implosion. Instead of firing two pieces together, compress a single plutonium core from all sides at once, forcing it into supercritical density. It sounded elegant in concept. It sounded impossible in reality. Nettermeyer knew it, and so did everyone listening. To compress a metal sphere with explosive force was like trying to push your hands evenly on a balloon while 10 hurricanes battered you from every angle. How do you make something explode symmetrically? How do you force chaos to behave? Most of the senior physicists dismissed the idea. They said the timing requirements were absurd. They said no explosive in the world could be shaped to produce perfect pressure. They said the theory was interesting, but the engineering was fantasy. But there were no alternatives. The plutonium bomb could not work without implosion. And so the idea that had been rejected as too radical, too strange, too unstable became the only path forward. Los Alamos split into new groups. One team continued refining the uranium bomb. Others were assigned to manage the overall physics. A small, often overlooked group was given the implosion problem. Their building sat away from the main cluster of labs. They worked with bits of metal, lumps of high explosive, models carved from brass and steel. They tested small charges that produced uneven shock waves. They shook their heads over graphite blackboards covered in complex equations. Nothing worked. Nothing came close. The early implosion tests were heartbreaking. They created hollow spheres from brass and fitted them with multiple explosive pellets. The theory was that if all charges detonated at the moment, the sphere would collapse inward. But every test produced the same result. The spheres bulged, cracked, twisted, or simply tore apart. The shock waves arrived at different times, colliding in ways that amplified distortions. Instead of collapsing inward uniformly, The shells collapsed in jagged fragments. Reports circulated through the laboratory describing the failures. Words like asymmetry, distortion, misalignment appeared again and again. The failures were not minor, they were total. Several scientists privately admitted that the implosion idea seemed impossible. A few even suggested abandoning the plutonium bomb entirely. In the classified hallways of Los Alamos, the whispers grew louder. We may never make this work. But Oppenheimer refused to abandon it. He told Nettermeyer and a small circle of scientists that they must continue. The entire project depended on them. They worked late into the night, often alone in their workshops, lit by a single desk lamp. They carved new shapes for charges. They tried different explosive mixtures. They invented devices that monitored the shock waves at microsecond intervals. Nothing changed. Symmetry refused to appear. By late 1943, the implosion group had become the grim corner of Los Alamos. Visitors walked past their tests and shook their heads. The uranium bomb looked inevitable. The plutonium bomb looked hopeless. Nettermeyer carried the weight of every failure. He felt responsible for the idea and the suffering it brought. He wrote in private notes that he feared he had led the laboratory down a dead end. But the truth was deeper. The implosion design was not failing because it was wrong. It was failing because the world had never attempted anything like it. Explosions wanted to expand outward, not inward. Physics resisted order. Nature resisted symmetry. To force a perfect implosion meant bending the laws of detonation into shapes they had never taken before. The challenge was bigger than any single scientist realized, and the failures were only beginning. Yet in those long nights of trial and disappointment, the foundations were being laid for a breakthrough that no one could yet see. Implosion looked impossible, but it was the only path, and the men working in that isolated corner of Los Alamos were about to discover their nightmare hit a solution that would change the world. In early 1944, the implosion group at Los Alamos entered what many scientists would later describe as the darkest and most demoralizing phase of the entire Manhattan Project. They had an idea on paper, an elegant mathematical concept in which spherical shock waves would converge perfectly onto a plutonium core. But the moment they tried to make the idea real, everything fell apart, literally. The first prototypes were small, crude spheres built only to test whether explosives arranged around a metal shell could compress it inward. These models were made from brass or mild steel, not plutonium. They were meant simply to answer the question, can an explosion be shaped? The scientists already suspected the answer might be no, but they had to try. They built hollow spheres with carefully machined thickness. They attached explosive charges at symmetrical points. Then they wired them together and stepped back as the test pits were sealed. The results were always the same. When the switches were thrown, the explosions detonated in a roar, and the test crew opened the pits to find twisted wreckage. Instead of collapsing inward, the spheres bulged sideways or tore apart at their seams. Sometimes only a single section collapsed. Sometimes the sphere cracked like an eggshell. Sometimes the charges fired at such uneven times that the sphere launched itself off the stand. The failures revealed a truth that many had feared, but few had said aloud. Explosives do not want to behave. They do not want to follow geometry. They follow chaos. Seth Nettermeyer, the father of the implosion idea, watched each failed test with a mixture of frustration and desperation. He believed the physics was sound, but making explosives behave like mathematical surfaces was something no one had ever accomplished. The timing had to be flawless. The pressure had to be equal at every point on the surface. The slightest difference, even a microsecond of delay, could turn a sphere into a lopsided wreck. The timing problem became the first villain of the implosion saga. The detonators used in early prototypes were noisy, unpredictable devices that could drift by tens of microseconds. To the human eye, such a delay meant nothing, but in an implosion, it spelled disaster. Shockwaves raced through metal faster than sound. If one detonator fired just a hair late, the shockwave arrived at the wrong moment and the entire collapse blew outward. One physicist described the problem perfectly. Trying to make a perfect implosion with ordinary detonators is like trying to conduct a symphony when half the orchestra refuses to play on time. The scientists built more prototypes. They increased the number of detonators. They changed the shape of the charges. They spent long nights chalking equations on blackboards. The chalk dust hung in the air like a symbol of their exhaustion. Nothing improved. Each test seemed worse than the last. The shells collapsed unevenly. Some flattened on one side and ballooned on the other. Some shattered into fragments. One test produced a sphere that folded inward like a crushed tin can. The scientists joked grimly that the only thing they had successfully invented was a machine for destroying spheres. John von Neumann arrived at Los Alamos to advise the team and offered a blunt assessment. He said the current models looked as if 32 hammers struck a ball at different times and expected it to collapse neatly. His critique was painfully accurate. The explosive charges acted like independent disasters, not coordinated forces. Each one created a shockwave that slammed into the sphere at its own speed. Sometimes they collided, sometimes they canceled each other out, sometimes they reinforced distortions, but they never converged perfectly. The scientists were stunned, not by failure, but by the consistency of failure. The pattern was so relentless that a quiet fear began to spread through Los Alamos. Some believed the implosion design was fundamentally impossible. Others worried that even if it was possible, they would not achieve it in time. The war in Europe was ending. The invasion of Japan loomed. Time was running out, and they were still stuck at the level of broken brass toys. Morale plummeted. The implosion team became a target of skepticism across the laboratory. Engineers working on the uranium bomb saw their work moving smoothly and assumed the plutonium group simply lacked engineering discipline. Chemists accused the physicists of misunderstanding shock waves. Physicists accused the engineers of using the wrong materials. No one agreed on how to fix the problem, but everyone agreed the problem was enormous. One scientist compared the situation to trying to design a camera while blindfolded, building it and then discovering it does not even resemble a camera when the blindfold comes off. The implosion sphere tests did not even hint at the clean compression required. They revealed a chaotic collapse that only confirmed how far they had to go. There were moments when the frustration boiled over. Nettermeyer suffered the most. Colleagues began pressuring Oppenheimer to remove him from leadership. They argued that he did not have the temperament or mathematical strength to manage such a complex problem. They said he lacked von Neumann's precision and George Kistiakovsky's explosive expertise. Some whispered that the implosion idea itself might have to be abandoned, but Oppenheimer refused. He understood that failure was part of discovery. He also understood that no alternative existed. The plutonium bomb had to use implosion. The physics demanded it. If they could not sculpt explosive force into a perfect sphere, the plutonium would pre-ignite every time. That meant the choice was simple: either make implosion work or give up on the plutonium bomb entirely. And giving up was not an option. Through 1944, the failures piled up, but so did the data. Each broken sphere taught something. Each misaligned shockwave revealed where timing had faltered. Each bent brass shell contained clues written in twisted metal. Slowly, patterns emerged, even if no one fully recognized them yet. The scientists began to realize that timing alone could not solve the problem. They needed to shape the shockwaves themselves. They needed a way to bend explosive force like light in a lens. They needed something entirely new. But they did not yet know what that something was. All they knew was that the dream of implosion was slipping away test by test. And yet the work continued,
because somewhere buried inside the failures was the path forward.
By late 1944, the implosion group had reached a breaking point. Every prototype sphere had failed. Every test model had crumpled or shattered. Every calculation seemed betrayed by reality. The lab was drowning in fragments of brass shells, twisted metal, burned wiring, and mountains of data that described failure in painful detail. The atmosphere in the implosion building felt heavy, as if the weight of the war itself pressed down on everyone inside it. But it was in this environment of exhaustion and despair that the most important breakthrough of the Manhattan Project finally began to take shape. The idea did not come all at once. It emerged in fragments, in chalk lines drawn late at night, in scribbled notes of shockwave diagrams, in arguments shouted across drafting tables, in failures that refused to be ignored. The key insight was simple yet radical. The problem was not only timing, it was geometry. The shock waves produced by ordinary explosive charges did not form a perfect spherical front. They curved unpredictably. They bent unevenly. They collided in ways no engineer could control. If implosion was ever going to work, the team needed a way to shape the shockwave itself. The concept was so bold that some scientists joked it sounded like trying to sculpt lightning with a pocket knife. But one man believed it could be done. George Kistiakowsky, a Ukrainian-born chemist with a talent for explosives, began to explore the idea that explosive force could be guided, bent, and directed the same way a glass lens bends light. If he could build an arrangement of explosives that created a perfect converging shockwave, then the plutonium core could be compressed evenly from all sides. The idea was simple in theory and impossible in practice, but Kistiakowsky believed in it with a stubborn intensity that surprised even Oppenheimer. He called the concept explosive lenses. The idea rested on a principle few in the lab had ever considered. Different explosives detonate at different speeds. Some burn fast, creating a sharp shock front. Others burn slower, producing a gentler wave. If these two materials were arranged in precise shapes, then the slower inner explosive could bend the faster outer shock wave inwards exactly where it needed to go. It was the explosive equivalent of how a magnifying lens bends light. To achieve this bending effect, the team needed layers of high-speed explosive and low-speed explosive cut into shapes so exact that even a fraction of a millimeter error could ruin the entire design. Kistiakowsky sketched the shapes on rough paper at first, then moved to wooden patterns, then clay mock-ups. The geometry grew more complex with each iteration. What began as simple curved blocks soon evolved into intricate multi-layered components, shaped like wedges of a perfect sphere. The scientists would eventually create 32 individual explosive lenses arranged around the hollow metal shell. Each lens would contain two explosives bonded together in a curved pattern. When detonated at the instant, the faster explosive would attempt to expand outward, while the slower explosive would hold it back, bending the shock wave inward. If the geometry was correct, the result would be a smooth spherical implosion. But the geometry had to be perfect. Los Alamos built an entire workshop dedicated to crafting and machining the explosives. Workers wore heavy aprons and labored with the precision normally reserved for watchmaking. The tolerance levels were microscopic. If one lens was even slightly misshapen, the collapse would fail. If the interface between the fast and slow explosives had a bubble or a crack, the shock wave would distort. The numbers involved were staggering. 32 lenses, dozens of parts per lens, hundreds of machining measurements. Each one had to be flawless. The laboratory introduced a new form of test known as RALA, short for radioactive lanthanum. These were small experimental implosions using a radioactive tracer. The tracer allowed scientists to measure how well a sphere compressed by analyzing the radiation emitted during collapse. It was a crude but powerful tool. For the first time, the team could see whether their shock waves were converging properly. The first RALA tests were discouraging. The tracer readings showed asymmetrical compression. The sphere squeezed on one axis and bulged on another.
Small imperfections in the lens geometry produced massive distortions. But unlike the earlier failures, these distortions were finally understandable. The data revealed not chaos, but patterns. Patterns could be corrected. Kostiakowski and his team refined the lens shapes again and again. They adjusted thickness, they curved boundaries differently, they changed the mixture ratios of the explosives, they experimented with new casting techniques to remove imperfections. The lens designs grew more complex, but also more controlled. For the first time, the scientists felt that implosion was not fighting them, it was beginning to cooperate. John von Neumann returned to study the new data. He traced the curves of the shockwave graphs with his finger and nodded. He saw something that had never existed before at Los Alamos: predictability. The shockwaves were beginning to behave like the equations said they should. The explosive lenses were working. The next Rala test changed everything. When the charges detonated, the compression curve appeared nearly spherical. The tracer readings showed symmetry that had once been unthinkable. The brass model recovered from the pit was not twisted or broken. It was only slightly warped. The difference was subtle, but monumental. For the first time, the scientists felt that implosion was possible. Fat Man was no longer an idea. It was becoming a machine. Nettermeyer, who had suffered the humiliation of early failures, watched the results in silence. Then he smiled a thin, tired smile. It was the first time in months that he allowed himself even a flicker of hope. The idea he had carried alone for so long had finally found its answer in the explosive lenses. The implosion team gathered around the data. They saw the result not as a partial success, but as a promise. If symmetry could be achieved once, it could be achieved again. And if it could be repeated, then the plutonium bomb might actually work. It might become real. They left the test site that afternoon exhausted but transformed. They were no longer wandering in the dark. They had found the path. And for the first time since the implosion nightmare began, the scientists of Los Alamos believed in something extraordinary. They believed the bomb could be built.
By early 1945, Los Alamos had entered a phase that scientists would later remember as equal parts hope and torment. The explosive lens design had given them their first real breakthrough, but turning that fragile success into a reliable weapon demanded an entirely new level of precision. Every microsecond mattered. Every curvature of explosive matter, every small mistake could ruin a months-long experiment. The pressure on the implosion team was enormous. They were racing against time, against the war, and against the terrifying possibility that the plutonium bomb might never work at all. The heart of the next stage was the Rala program. The Rala tests used small amounts of radioactive lanthanum to measure the degree of compression inside implosion models. When the lenses detonated, the radioactive tracer emitted bursts of gamma rays. Sensors around the test pit captured these signals, revealing the exact shape and timing of the collapsing sphere. In crude terms, Rala allowed scientists to see inside an explosion. The first Rala tests after the lens breakthrough were cautiously optimistic. The gamma curves showed partial symmetry, better than anything the lab had recorded before. But partial symmetry was not enough. A real implosion had to push the plutonium core into supercritical density in less than a microsecond. Anything less than perfect convergence would cause a fizzle, a failure, a disaster. Every few weeks, the scientists drove out to the remote test site. Trucks carried carefully machined explosive lenses protected in padded crates. Technicians set up the lead shielding and radiation detectors. A small sphere made of metal or resin stood at the center of the pit, replacing the plutonium core. The team wired 32 detonators around the sphere, each linked to master firing lines. Then came the countdown. A siren wailed through the mesa. A blast of wind swept the dry earth. The detonators triggered. A flash. A dull thump. A plume of dust rising into the air. And then silence. The scientists would gather in a bunker nearby as the instruments spat out their readings. More often than not, the results brought only disappointment. The compression curve would show a slight bulge, a timing offset, a wavefront that arrived too fast or too slow. A tiny imperfection in one lens would ruin the entire test. A single detonator firing microseconds late would destroy symmetry. The failures were not spectacular. They were quiet, invisible, mathematical, but they were crushing. Kistiakowsky often paced back and forth across the concrete bunker floors, muttering calculations under his breath. Von Neumann scribbled corrections on his chalkboard in furious bursts. Neddermeyer stared at compression graphs until his eyes throbbed. The implosion team lived inside a cycle of hope and panic. Each test was a chance for triumph and a threat of humiliation. The pressure wore them down. Oppenheimer visited the test site often, walking slowly with his hands clasped behind his back, his face drawn thin from sleepless nights and the weight of leadership. He spoke gently to the team, but he understood the stakes better than anyone. Without the implosion bomb, the Manhattan Project would lose half its purpose. Without Fat Man, the United States would have only one workable atomic weapon. And no one inside Los Alamos believed that one bomb, Little Boy, would be enough to force Japan into surrender. That knowledge hung over every Rala test like a storm cloud. As the failures continued, tension inside the laboratory sharpened. Some scientists began blaming the geometry, others blamed the casting methods, others blamed the detonators. The implosion team was exhausted. They slept little, ate irregularly, and lived in a blur of calculations, drafts, and detonations. The stakes of every mistake grew heavier. At one point, a Rala test failed so badly that the tracer readings showed almost no compression at all, a complete collapse of the shockwave geometry. When the data was brought to Oppenheimer, he closed his eyes for several seconds, then simply said, "We test again." That became the mantra of the implosion team. Test again, build again, fix again. There was no other path. There was no escape. Slowly, almost painfully, progress emerged. A lens casting method improved. A detonator design stabilized. A predicted distortion disappeared in the next test. The graphs began to show cleaner curves. Not perfect, but close. Kistiakowsky pushed his men harder, insisting that every minor flaw be treated like a catastrophe because, in an implosion, it was. The detonator problem remained the greatest obstacle. Early blasting caps were too inconsistent. Their firing times drifted by microseconds. The scientists needed detonators that could fire with perfect simultaneity. The search for such a device led to the development of the exploding bridge wire detonator, invented by Luis Alvarez and his team. When it worked, it was revolutionary. It fired using an electrical shock instead of chemical burning, producing an incredibly precise detonation pulse. The first test with bridge wire detonators revealed major improvement. The shock wave arrived more uniformly. The compression curve at the pit looked like a sphere instead of a crushed egg. It was not yet good enough, but it was closer than anything the team had ever seen. The scientists dared to hope. Then one morning in early 1945, a Rala test produced a compression profile so nearly perfect that the bunker erupted in applause. The curve was smooth. The symmetry was above 90%. The model collapsed inward instead of sideways. The tracer readings showed convergence that matched the theoretical predictions. Neddermeyer cried quietly in the corner. Von Neumann smiled for the first time in weeks. Kistiakowsky stood silently staring at the curve, as if it might disappear. But even this was not enough. They needed more tests, more data, more proof. Implosion had to work reliably every single time. It was the difference between victory and failure, between a functioning bomb and a worthless fizzle. Every scientist knew that a single mistake on the real device would not mean a broken sphere. It would mean a catastrophic failure of the entire project. So they continued testing, pushing themselves past exhaustion, through wind, snow, heat, and endless nights of recalculation. The failures hurt, the successes came slowly, but the trend was undeniable. Rala, curve by curve, the impossible was becoming possible. The team could feel the finish line approaching, even if they could not yet see it. They knew that somewhere ahead lay the moment when they would be ready for the ultimate test, the day when the implosion bomb would no longer be theory or hope or failure, the day when it would prove itself in fire.
By mid-1945, the implosion team stood on the edge of either triumph or disaster. Years of failures had scarred them. Endless nights of recalculation had drained them. The pressure of knowing the future of the war hinged on their design weighed on every breath they took. But something else had begun to rise beneath the exhaustion, a quiet confidence, a sense that after all the broken spheres, all the failed Rala tests, all the detonators that misfired, and all the shockwaves that twisted instead of converging, they were finally approaching the impossible. The breakthrough came not in a single moment of revelation, but in a steady tightening of precision. The explosive lenses became cleaner, more exact. The casting process improved. The slow and fast explosives bonded with fewer imperfections. The assembly crews learned to shape the lens surfaces with the careful hands of artists. Bridge-wired detonators began firing with remarkable consistency. Each improvement felt small, but together they formed the core of something extraordinary. The scientists gathered in the analysis room after each test, watching the compression curves unfold on paper strips pulled from the detectors. At first, the lines buckled, distorting into irregular patterns. Then they smoothed. Week by week, the curves approached the symmetry the design required. The day a Rala test showed a nearly flawless convergence, the room erupted into a celebration so loud that nearby technicians feared something had gone wrong. It was not perfection, but it was close enough to prove one thing. Implosion was no longer a dream, it was a functioning mechanism. With this success, the laboratory turned to the real weapon. The plutonium core had been machined with astonishing precision. Its halves were polished until they shone like gray mirrors. The tamper shell surrounding it had been fitted and refitted to ensure no gaps existed. The lens assemblies were molded, tested, and remolded. Each firing circuit was checked again and again. Every component carried the weight of years of failure and the hope of a successful future. Yet, for all the scientific triumph, the emotional weight of the moment was immense. The men who had struggled through so many failures now faced the ultimate test. They knew that if implosion worked, it would unleash a force unlike anything the world had ever seen. If it failed, the consequences would be seen not as a scientific setback, but as a collapse of the entire Manhattan Project. And the war would continue with unimaginable cost. Oppenheimer gathered the lead scientists shortly before the full-scale test. His voice was calm, but every word carried gravity. He reminded them how far they had come, how impossible the task had once seemed. He reminded them that they were about to step into a new world, and that once they crossed that threshold, nothing would be the same again. The men listened in silence, some with arms folded, some with hands clasped behind their backs, and some with faces pale from the enormity of what lay ahead. Then Oppenheimer said the words that echoed through the room. "The design is ready. We proceed to Trinity." Preparations for the Trinity test began at the Jornada del Muerto desert. The implosion device, now named Gadget, was assembled in a makeshift tower under strict security. Scientists and soldiers walked across the sand, adjusting cables, checking circuits, tightening bolts. The lens layers were installed. The electrical systems were armed. The plutonium core was placed inside its shell in a quiet ritual performed with steady hands and solemn faces. On the night before the test, the desert air was cool and still. Lightning flashed on the horizon, though no storm came near the site. The scientists slept little. Some wrote letters to their families, others walked alone in the darkness, lost in thought. A few gathered in small groups, speaking softly about what they hoped and feared. No one truly understood what would happen when the switch was thrown. They had predictions, formulas, spreadsheets, but the truth lay beyond numbers. This was the first implosion weapon ever built by mankind. No one had ever seen such a device in action. At 5:30 in the morning, the countdown began. Men took their positions in bunkers miles away. Others waited in observation shelters. The final safety checks were completed. The circuit became live. The firing command was issued. A pulse raced through the cables into the detonators. 32 bridge wire charges fired in the same instant, sending shockwaves into the lattice of explosive lenses. The lenses bent the shockwaves inward, curving them into a collapsing sphere of pressure. The plutonium core reached critical density. And then the world changed. A searing light, brighter than dawn, rose above the desert. The observers shielded their eyes as a fireball expanded in a fraction of a second, climbing upward in a column of blinding radiance. A shockwave rippled across the desert floor. The sky glowed in colors no sunrise had ever produced. The heat was felt miles away. The men watching stood transfixed. Some gasped. Others murmured words they did not remember later. Oppenheimer whispered a line from an ancient text that would become forever linked to the moment. But the scientists who had fought for implosion felt something different, something quieter and more personal. They had done it. After years of failure and doubt, the implosion design worked. The explosive lenses had shaped the shockwave perfectly. The core had compressed exactly as planned. The weapon had ignited with a power beyond imagination. Their calculations had become reality. Their nightmare had become triumph. But as the mushroom cloud rose into the sky, every man present understood the terrible truth beneath the achievement. They had opened the door to a new age, an age that could not be closed again. The war would end, but the world would never return to what it had been. The scientists had proven that implosion was possible, and the consequences of that discovery would echo for generations. The early prototypes had failed again and again. Many believed the plutonium bomb would never work. But the failures had led them here, to the blinding moment in the desert when science reshaped history. Trinity had proved that the impossible was real, and Fat Man would soon prove it to the world.